The last section we're going to talk about with nuclear radiation is talking about fission and fusion. And this is probably the most common for everyday life that you might have been familiar with. Nuclear fission really came around when they started doing research on the atomic bomb. What they noticed is that if they took a large nucleus, such as uranium, that's the most common one we use, mainly because it's for power plants and stuff like that too. Bombard it with a small particle like a neutron, the uranium then breaks up. To remember this one, fission is very much like fizz. So the uranium is actually fizzing off and it's making smaller things. The nucleus splits into smaller nuclei, and then several neutrons are also given off. And then those neutrons go back and hit more uranium, and it just keeps going. When that happens, large amounts of energy are released, and that's where we get the atomic bomb from. So, when a neutron bombards uranium-235, this splits up. When that happens, large amounts of energy are released. It produces two smaller things. Instead of just having one, it actually produces several little things. So two separate elements. It also produces more neutrons, which then react with more uranium. So here's our uranium. The one neutron hits it. Notice 1 and 235, it creates uranium-236 in the process. This number down here didn't change, just the top number. And then that creates so much energy, or that's so unstable that it then breaks down into smaller categories. So 1 krypton, 1 barium, and then 3 more neutrons, and a lot of energy. And then those 3 neutrons then hit 3 other uranium-235s, and it happens all over again. Now, where does the energy actually come from? Well, if you were to actually take the time, or if we actually had the ability, to weigh the before and the after, what'll actually happen is this part over here weighs less. Even though, according to our equation, it should weigh the same. But it's a very, very, very small difference in weight. That small difference in weight goes into this equation, which you may be familiar with Einstein. E equals mc squared. That's his most famous equation. And that's the equation he came up with when he was working on the atomic bomb. So it's an extremely small amount of mass, but because of this, that's the speed of light, 3.0 times 10 to the 8th. That is then squared. So a small amount of energy is multiplied by this squared, produces a lot of energy. So that is where that energy is coming from. 1 gram of uranium is the same amount of energy as 3 tons of coal. But there's a lot of other issues that go along with that when we're talking about using fission for multiple purposes, such as nuclear power plants. Such as, what do you do with the chemicals when they're all gone, when they can't use them anymore? Or where do we get the uranium from to begin with? So there's a lot of other issues involved. So, to do these equations, do them just like you would any other nuclear reaction. The left has to equal the right. So, if I look at the top one first, we have 1 plus 235. The arrow means equal. 137 plus x, because we don't know what that is. We have 2 neutrons here. So actually it's 2 up here and 0 down here, because 2 times 1. And then energy. So we gotta solve for x. So that's 236 is equal to 139, because 137 plus 2, plus x. So 236 minus 139. 97 is our top number. The bottom number, 0 plus 92, is equal to 52 plus x. It's a 0 down here, so 2 times 0 is 0. So 92 minus 52 is 40. That's going to be our x. So you will look on the periodic table to figure out what 40 was. And that actually ends up being ZR. Now I mentioned earlier that uranium is what we use in nuclear power plants. Just to give you a brief overview of how nuclear power plants work. Here is where the chemical reaction actually occurs. As we said before, the uranium is bombarded with a single neutron. And then when that happens, three more neutrons are given off. And then those 3 hit more uranium. So it causes a chain reaction, and that chain reaction is happening right here. Now, in order for it to stop moving, they have these things called control rods that they lower, and then they absorb all these extra neutrons that are being given off. And once they're absorbed and controlled, the control rods go back up, and the reaction starts up again. The heat that's formed here heats up water here to form steam. This then turns a turbine, it turns a motor, which then produces electricity. And then the water comes through, and it cools back down, and it goes either back into our system or into area water. The reaction itself that's actually heating up the water goes right back into it. The other type of nuclear reaction is nuclear fission, fusion. Now once again, let's break this word down. Fuse. We're fusing things together. We're putting things together. This one in particular, 2 hydrogens are coming together to make a helium. And this is actually what's happening on the sun right now. Eventually we're going to get to the point where we run out of hydrogen on the sun and there's nothing else to fuse, and that's why they refer to it as a dying star. It combines 2 small nuclei into a larger nucleus. And then when that happens, once again, a lot of energy is released. And that's how fusion occurs. And that is the end of chapter 9.